So in this part two of the crash course, I wanted to develop the theme that I started previously talking about solvability of equations in fields. I want to talk about that in at least two different senses. There are two ways that I can think of to have problems solving equations that might motivate us to think about field extensions, which is where we're going with this. The first is size. So in the last video, I showed you guys that FP is a field for every prime P. This enables you to solve linear equations, right? Because if you have any AX plus B in this field equals Y, then I can solve it for X because there will be some A inverse, right? You could even think of this as like a fraction. And like that's all cool and good for linear equations. Why did that happen? But what about higher degree equations, right? And in general, how many equations can you make in a field? Well, up to scaling, right, dividing out by some leading multiple that doesn't really matter because they always have multiplicative inverses, there are going to be degree of the equation, let's call the thing f, right? Whatever the degree is, that number minus 1 will be the number of parameters that you have to deal with, right? Like if you have a quadratic equation, that's degree 2. Oh, sorry, that's not right. Even it's plus 1 again, because while the first term is fixed, there's also a constant term. So there'll be exactly degree f many parameters. And so if I have p things, there will be p to that many total equations possible. And you can't expect this very fast growth to be kept up with by just FP. Like, why would it be that FP just contains solutions to all of its equations? And we can check this, like, with some degree of explicitness. So let's think about a simple FP. How about we look at a small one to really show the example? And we look at some quadratic equations. How about just x squared plus 1 in FP? Let's say I want to solve that equals to 0. So there are only three things that could possibly work here. I have 0, which gets me 0 squared plus 1, which is 1, not 0. I can try 1, which is 1 squared plus 1, or 2, which is not 0. And I can try 2, which is 2 squared plus 1. 2 squared is 1 in FP because it's 4, and 4 is equivalent to 1 mod 3. So that's 2, not 0. And so this issue of size means that most of the time, equations in FP are not solvable. And so that's a problem, right? That would be something that we'd like to rectify. The other situation is just good old algebra reasons. For example, we know that when we're working with Q, Q is sitting inside of R, where the quadratic equation holds. Maybe you were asking yourself before, could I do the quadratic equation on this? That's a great question. Hold that thought. In R, where I do have the quadratic equation, there are at least two more ways that things can fail. The first is I can look at things like x squared minus 2, which we know the solutions for. In R, there's plus or minus the square root of 2, but not in Q, right? This isn't something in Q. This is irrational. So that's a problem for us. The other issue is sometimes there just aren't solutions even in the bigger field, like x squared plus 1. This has imaginary roots. Not even real. And so there can be different kinds of failure depending on what the kind of equation that you're dealing with is. And all of these seek to be rectified. just to say something really briefly about the quadratic equation in FP. Great question, hypothetical student. Writing x equals minus b plus or minus the square root of this guy over this guy. Right? In order to do this, the issue is the square root. Which elements actually have square roots in FP? Right? In order to make that work, kind of what I'm doing here is I'm telling you that x squared plus 1, right, in FP, that's the same thing as x squared minus, or sorry, in F3 in particular, that's the same thing as x squared minus 2. So what I've proven here is that 2 does not have a square root. Maybe I should say what we saw is equivalent to 2 does not have a square root. Sound familiar, right? We talked in groups and group theory a lot about which elements do and don't have square roots, right? A common and recurring theme when dealing with algebra. And so the question of which elements do have square roots in which FPs is an answered question. It belongs to number theory. So maybe a direction for future reading if you're interested is number theory, and in particular, the study of what's called quadratic reciprocity. But we're not going to have time to pursue that in our little mad dash here. Okay, so I've shown you now 2 reasons why fields can fail to have solutions. One more point about all of this is that even though this failure is possible, and it can be messy, right? Like there can be different degrees of failure depending on the issue. On on Q in particular, Q sits inside a big field C, and C has the property that every equation of degree D has exactly D roots counting multiplicity. This is the famous fundamental theorem of algebra. And actually, I'll prove this for you guys in a handful of months when we do complex analysis. That's my favorite proof, at least. And so we have a ways to go between now and then, like a couple of other classes. But rest assured, you will come to understand this in due time. But if you remember anything about real analysis, then you know in the back of your head that real analysis is significantly harder than just this basic question about factoring, right? Like there's all this stuff about how to set up the real numbers and topology and sequences and so on, and it's all kind of lurking in the background. And so you might ask yourself, do I really need all of this in order to solve simple equations, right? Do I need C? The full construction just to understand equations? And the answer is no. This is going to be the point of the theory of field extensions. Every equation, every polynomial, I've been saying the word equation, but all the time I'm talking about polynomial equations. Every equation is solvable in some field extension. Actually, what I said is true, even if it's not a polynomial equation, if I'm willing to deal with nasty field extensions. But our field extensions are going to be simple. Okay, I think that's probably enough for this segment. We've been once again going almost 10 minutes, and there's still one more little batch of things that I want to share with you. So I think we stop this discussion here, and then we're going to pick up with one more part talking about homomorphisms, and then we'll be finally ready to pick up with Pinter. Sorry about all of this. I didn't really realize, I guess, just how much Pinter had spread out over the chapters on rings rather than introducing them in their own dedicated place. So I guess it's a little bit my bad. But thanks for bearing with me.